Oh, sorry. Hello, everyone. Welcome back to the Double Ish YouTube channel. And this is part of the good stuff. And I am super happy to have Anna Schauer with us today. Hey, Anna.
Hi, thank you so much for having me. I'm excited to talk about my research.
Well, thank you. It's a very lovely article and a very topical one on this particular object. So it's very cool. Anna, where are you at?
I am at UT Austin, or
Okay.
generally in the universe.
Generally, there we go. That's a good place. Let's see, summertime in Austin, so you're probably getting the Gulf humidity rolling on up and getting some moisture there.
Oh yeah, it's hot outside.
Yeah.
Like it starts to decline a little bit. So like sometimes now in the afternoon we have like below 100,
Ooh, it's
which is
probably
good.
probably when the rains come as well. So yeah, we get a lot of the same stuff in August in Phoenix. That Gulf moisture rolls up, and this is when we get our monsoons and all of our rain. The desert rains come in the summer. Actually, it's very cool. You know, when I first looked at your background, I thought that was it's a very interesting kind of stained glass art piece there. But upon further inspection, it's actually a cosmological simulation and a zoom in of stuff. So very cool background.
Thank you. That's actually my own simulation set.
Very nice.
So yeah,
Very cool.
I
Very
used
cool.
it for the first Stars conference.
Oh yeah.
And yeah, I just love it.
Yeah, yeah, very beautiful. And presumably that'll do something with what we're going to talk about here. So,
Absolutely.
so speaking of that, Anna, what do you like to do for research?
So I am interested in the high Redshift universe.
Hmm?
And for me, that means anything really up to Redshift 30-ish. So yeah,
Darn.
currently I'm working on a project that was kind of low Redshift for me, so down to Redshift 5, but
Ooh.
that's
You are high redshift.
that's
Very
as low
cool.
as it go. Yeah.
Actually, it goes lower, but you know, you can start at z equal 5. It's fine. Very cool.
Yeah, so I do computational astrophysics.
Mhm.
And yeah, at like the very high redshifts, I think it's hard to even distinguish is it like galaxy formation or star formation what they do, because those mini halos are so small. We typically
Yeah.
have like one star forming region. And I'm interested in population 3 stars, so the first stars that formed in the universe. The yeah.
Maybe we caught one. We'll find out here.
Maybe, yes, that would be so exciting.
Oh, when we get there, let's go ahead and start in on this topic. And this is an APJ letter. It's open access, people, so you can go ahead and get it for free. Go grab a copy. And on the probability of the extremely lensed Z equals 6.2 Earendel, source being a population 3 star. And Anna, take us away.
Thank you. Yeah, I'm very excited to share this with you. I wrote this paper with my amazing co-authors, Volker Brom, Yves Drory, and Mike Bolen-Kolchen, all here at UT Austin. 3 of us are actually German, so like
Okay,
we have
German
a little
Austin connection.
accumulation here.
There we go.
Yeah, and yeah, we're excited because like we read this paper from Walsh et al. 2022 about this extremely lensed star. And they're pretty confident that it's a star because it's such a small radius. And they are able to see this at redshift 6.2 because it's so strongly lensed. It has a magnification of like 1,000 to 40,000. And therefore, yeah, it is like an amazing view into the early universe. Yeah, and since we're interested in the first stars, we're just like interested, could this be a first star? Or is it more likely like a accumulation or a single population 2 star? So
Yeah.
yeah.
Yeah. So I think the other amazing thing about Earendal is that it's persistent. Because you do get micro lensing events where you know things will brighten by a factor of 1,000 or so, but they're short. And this one, as far as we can tell, is persistent. It's staying there, and so that's really really important.
Yeah.
Very cool.
So I think you've observed it over like a couple of years and it just stayed there and stayed there and stayed there. And I've heard like a little birdie called Twitter saying it has been observed with JWST. So very, very excited for those results. Well,
It's going to be very cool to see this develop over the next couple of weeks. This is very topical material. Very cool.
Yeah, and one of the reasons we're so interested in this object is because, like, I'm a computational astrophysicist, and there are a few of us just like working on the early universe, but it's really, really hard to get any observational constraints.
Yeah.
So what people do is they use 21 centimeter radiation to get like the signal at redshift, like, yeah, down to reionization basically, but
Yeah.
it starts at higher redshift, so like around the redshift 20, but then we can get like a global signal of what is happening in the early universe that does not constrain our POP3 IMF very much. And then the other thing is that we didn't find a metal-free star yet, neither in our Milky Way nor in close by galaxies.
Yep.
So that kind of gives us a lower mass constraint on the POP3 IMF by saying, oh, like if we had POP3 stars, like we would see them, like they can't be like super low mass because otherwise they would survive from basically cosmic microwave background until now. So this gives us a lower limit of 0.8 solar masses, or even sometimes 1 solar mass as the lower limit of the POP3 IMF.
Yes.
So now having like a single object observed at redshift 6.2, like of course it's hard because it's magnified. This is the only way why we are able to see it. It's extremely magnified. And then it's hard to disentangle what the absolute magnitude actually is. I think it ranges from 38.7 to 34.7. So it's a huge like spread that just comes naturally with like the magnification uncertainty. But it is exciting, and this might be like very close also to the limit that we predicted for the ultimately large telescope of 39 AB magnitudes. So yeah, we read this paper. We read this paper in very much detail, and we were like, okay, can we actually say something about the probability of this object being a POP3 star?
Yes.
And it turns out we can't say it like definitely, but what we did was we find a probability as a function of the mass of the object.
Okay.
So if you scroll down a little bit,
let's take a look at
this is a short paper. So we built basically a model how we can mimic the probability of Earendel being a POP3 star. And we had 3 big components that went into it. One is like, how probably is it that we actually have pockets of pristine gas and like first stars still at this high redshift of 6.2. So this is like this little FPOP3 factor that comes into here. And then, of course, like how many host halos do we have? Like the host halo function plays a role. And then we have the fact that high mass stars live for a short amount of time. So if we go to the like high mass regime, then we need to account for that. Like if we just like look at the sky, we're more likely to find a low mass star than we're likely to find a high mass star. So that gets factored in. And then the big thing is the initial mass functions of both POP3 stars and POP2 stars. And this is what gives us like a relatively high probability of it being a POP3 star. Because the allowed mass range for Earendel is between roughly 50 and 500 solar masses, so the white part that you see here. And while the probability fraction that we have
Got it.
like pristine pocket, like it drives us down in probability. Like I think it's below 1%. The IMF actually drives us up, and that is good, and that is wanted, and yay.
You.
Yeah. So yeah, what we assume is for the POP3 IMF to be more top heavy, and we choose two different IMFs that kind of like are an upper limit and a lower limit for what people do in the literature for POP3 IMFs. One is a log normal IMF that you can see here in light blue. And the other one is a Larsen IMF, but the Larsen type IMF with a characteristic mass of 10 solar masses.
Okay.
So you see that this is like bent over, and but then at the like has kind of the same slope. Whereas for the POP2 IMF, we choose the standard Larsen POP2 IMF. So as you can see that with the pink lines there. And usually the POP2 IMF extends out to like 100 solar masses or 150 solar masses. But then the answer is clear, like we have like if we just cut off the POP2 IMF at 100 solar masses, and Earendel has a mass higher than 100 solar masses, it is a POP3 star, but then we didn't like gain much from our calculation. We just put everything in. So we actually studied a case that we have it over the full mass range, similar to POP3 stars, extending from 0.1 to 500 solar masses at the low at the higher end, which I think is never really used in the literature. And in addition, we have a model where we cut off the POP2 IMF at 150 solar masses with an exponential tail. And that is like to mimic that we absolutely do not observe stars of a mass of like 300 solar masses. I think there's like a handful of stars that has a mass of higher than 150 solar masses. I think the biggest one is Westerhout 49-2 with 250 solar masses, but like an error bar of 100. So yeah, like we really don't observe those like very, very massive POP2 stars or POP1 stars. Therefore, we add this cutoff, this exponential cutoff at 150 solar masses, where this drops down. And then basically from this figure here, where you can see all those three things convoluted into each other, we can already derive the probabilities. And that is basically by dividing each of those lines with each other. So like, the probability that it is a star, we set to 100%. And then we can estimate the fractions for that. Yeah, and that already leads us to figure 2 where we did this. So we see here the probability as a function of the stellar mass. Now again, the allowed range is in white, so from 50 to 500 solar masses. And we have all the POP2 probabilities with dashed lines. We have all the POP3 probabilities with solid lines. And then we consider the log normal, the Larsen model, and also the cutoff and the not cutoff. And you can see, first of all, when you have the not cut off, so if you assume that POP2 stars can form all the way out to 500 solar masses, which we honestly don't, then this probability stays quite high of it being a POP2 star, and the probability of it being a POP3 star like reaches 10% in this log normal IMF model for POP3 stars, and at least has 2% for like the other model where we assume like Larsen IMF with a high characteristic mass. So still like even if this is true, we still have like a more than a 1% chance of having detected a POP3 star, which I think is amazing.
Right. Yep. And we go a lot higher than that.
Yes, we go a lot higher than that when we actually choose the POP2 IMF that we think is a little bit more realistic, where we like have this exponential tail for the POP2 stars beyond 150 solar masses. So then those are the green lines. The green dashed lines just like plummet, and the POP3 probabilities take over at around 300 solar masses. So then, and it really evens out at like 100% probability when you reach the highest mass end of 500 solar masses. So it's super exciting.
Let me just ask, how might this change if, let's say, Earendal is a binary?
So if Earendel is a binary, the thing with POP3 stars is above a certain mass, the flux is quite similar from like it's 2 POP3 stars or it's 1 POP3 star of a higher mass. So this has been done very early on, 2001, I think, by my co-author Volker Brom. So we see like a very similar light curve, just like adding up to 100 solar mass spectra is basically the same as 1 200 solar mass spectra.
So it's would actually still be very interesting if it turns out that Earendal is a binary of 2 stars. That's still very interesting.
Yeah. If the combined mass of the binary is like 500 solar masses, then I think it's still a POP3 star.
Yeah. Very cool.
Yeah.
Very cool. So the takeaway is it's a pretty good probability that it's POP3.
Yeah, I would say it's a good probability above like 200 solar masses, and it's an extremely good probability above 300 solar masses. And if it's more 50 solar masses, then I guess it's still a POP2 star. So we don't know. It's hard because of like, we know the magnitude times the magnification. So but luckily there are ways to find out with JWST if a star is a POP3 star or not. So we're excited for that. Like there has been like certain POP3 diagnostics, like first by Brom in 2001 again, but then also by a very recent paper by Nakajima and Maiolino, just like this year. And one big prominent feature of POP3 stars is that the helium-2 line has a large equivalent width. It's larger than 20 angstroms roughly, and it is combined with a high helium-2 to H-beta line ratio. So this is like a very strong indicator that it is a POP3 star. Like this parameter space is basically not occupied by POP2 stars or any kind of AGN contribution. So we will find out. And then in return, when we know, it will be amazing because either way, we have found maybe a very, very massive POP2 star, which tells us something about POP2 stars.
Yes.
Or we have found a POP3 star. And then when we know the mass, then we can have constraints. The first time a high mass constraint on the IMF of POP3 stars. So we are thrilled.
Anchor point. Very cool. Awesome. Well, this calculation definitely needed to be done, right? So you got one, looks good. What's the probability of it? So very cool. So
and the original authors had it like mentioned in their paper, but we were like, let's do this calculation.
I'm sure this will not be the only one. If it turns out to be one, there'll be several of these. So it's very cool. So Anna, thank you so much for sharing this very exciting APJ letter. Very nice. And I think, sort of this topic is all about the future. So So why don't you let's go ahead and speculate a little bit. Let's say it is let's say it is a POP3. Where do you think we go over the next couple of years then with this? Is there maybe a possibility if its probability is pretty high, maybe there's a possibility of getting another caustic, maybe it's not the only high redshift star or other instruments, or what theory will say about this going forward, both on the stellar side and on the cosmological formation side. They're both playing in there. So let's assume that it is a single star. And where do you think we go over the next couple of years?
So I think if it is really a single POP3 star, there will be many papers written about one star.
Yes, there will be. There definitely will be.
Like trying to constrain both the shape and the upper mass end of the IMF just with this like one data point that we have. I think we have the chance of maybe getting a few more extremely lensed objects, but I don't think we will get like the full population of POP3 stars from those extremely lensed objects. I think we were very, very, very lucky to observe this one. And yeah, thank you, universe, for having this like
once in a while it smiles.
Yeah.
That was okay.
Very cool. Like definitely like theorists will continue to investigate POP3 stars from the computational side. Like there has been a little bit of a debate if the POP3 IMF is really that top heavy or a little bit less top heavy with simulations, like the ones that are able to resolve things so exactly to like I think 10 to the 18 particles per cc. That is amazing, but those simulations are so expensive, they can't run for very long. So we don't know if those seeds can continue to grow for a longer time.
Yeah.
So yeah, I think like more from the computational side will be there for sure. Then there are effects of the high redshift universe that we need to take into account, and we need to take them into account more. One you can see in my background. So that is the so-called streaming velocity, where we do have this large scale velocity imprinted in the universe between dark matter and baryons. And then when you're like in a region with a high streaming velocity, everything is a little bit washed out and you form like stars later, the baryon fractions are smaller. So like the standard case of the universe is probably somewhere here. It's not here, it's somewhere here. So like most of the universe has a streaming velocity. It's important at high redshift. But then if we want to look at like the very, very long term, we actually wrote another paper that we called the ultimately large telescope.
Okay. Ultimately large.
Yes, ultimately, because it finally reaches like POP3 stars.
Got it.
And is designed to like see a lot of POP3 stars.
Okay.
And
characterize population.
Yeah. So like we can write more papers about more than one star.
There you go. Population synthesis.
Yeah.
So how large is ultimately large?
100 meters.
100 meters. Okay.
Yeah.
It's not outrageous. It's good size.
Yeah. And then there was like a very nice paper by Roger Earandal and his collaborators about liquid mirror telescopes on the moon. So
that one. Yes.
I hope for that.
Cross fingers. It will be very exciting over, let's say, the next few weeks or the next few years on this topic as we watch this evolve. So very cool. So Anna, thank you so much once again for chatting about Earendal and the implications.
Thank you so much for giving me the chance to talk about my science.
Everybody loves to talk about their papers. We get so rare a chance to actually talk about our papers, right? The thing that we put so much time and effort into. Rarely do you actually get to talk about the paper as it stands, right? So usually you kind of figure out and you put it in a talk and you go, but that's not quite the same as talking about the article in depth or as much.
I think it's more often that other people talk about your papers during journal clubs.
Yeah, and here you get to see who the author is, and you get to hear what the author thinks about their paper as opposed to somebody else. So it all works fairly well. Very cool. So thank you. And everyone, this will do, and I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.